So this video is gonna be a little bit technical. This is an interesting topic. It's very related to machine learning and just multiplying matrices together. So I can just make this a little bit bigger. Great. I don't know a lot of vocabulary here, but we're gonna go through it, and then hopefully we learn something by the end of the article. So the article is from Sibo HM, if I'm not wrong. Okay. Okay, so from Simon Boehm. Excuse me if I'm not pronouncing that correct. So he's done these past projects. I built and maintained the fastest open source decision tree compiler. It's a fairly simple LLVM based compiler. The speedups come from careful instruction cache blocking and lots of smaller tweaks, like bit vector based encoding of categorical decision nodes. It works well enough but should really be interpreted instead to help with the cache bottleneck, so I'll rewrite it eventually. Alright, I implemented many important algorithms for distributed deep learning, data parallelism, gpipe, interleaved backprop. To understand them better, the resulting library is called shallow speed and runs on CPU using plain NumPy and MPI. I published a Neuro IPS paper where we train a deep learning model to predict the effects of drug molecules based on large single cell RNA sequencing datasets. Alright, he knows what he's talking about, so I guess this article is a good article. Okay. Fast multidimensional matrix multiplication on CPU from scratch. Okay, NumPy can multiply two 1024 by 1024 matrices on a 4-core Intel CPU in around 8 milliseconds. This is incredibly fast considering this boils down to 18 flops per core per cycle, with the cycle taking a third of a nanosecond. And NumPy does this using a highly optimized BLAST implementation. Oh great, he actually links this for us. He explains it here. BLAST is short for, let me make it bigger. BLAST is short for Basic Linear Algebra Subprograms. Just gonna rewrite this, so short for Basic Linear Algebra Subprograms. These are libraries providing fast implementations of example matrix multiplications or dot products. They are sometimes tailored to one specific family of CPUs like Intel's MKL or Apple's Accelerate. Oh, I didn't know that. However, non-vendor specific implementations like OpenBLAST are also available. Pretty interesting. Alright, so as you heard it, matrix multiplications and dot products. How hard is it to recreate performance that's roughly similar using plain C++? For simplicity, let's assume both matrices are square. For each data entry of our n times n result matrix, we have to perform a dot product between a row vector and column vector, both of length n. So matrix multiplication, I guess here. We have matrix A, matrix B. So it's not dot product anymore, you see. I don't remember this, but matrix multiplication was row by row. Am I right? So it was like this, and then this, and then it was this, and then this, and then this. Okay, maybe we can figure it out from here. For row in range 8 dots n rows for column, this column for inner. Okay, he's basically multiplying now. It's not dot product in there. The result is n cause rows, n columns, n dot product. Oh, okay. That's the time complexity that he's giving us. 2 multiple plus is he explaining it? Because you multiply, then you add it up. Sure. You have 2 and yeah, makes sense. Running on a physical machine in NumPy, the code for example looks like this. So you can see that. Excuse me, my monitor has too much light. My eyes are watering. What have I done? Okay, let's go down. Much better. Okay, so in NumPy the code for example looks like this. Make 2 to the 10. I don't know why 2 to the 10 is easier than saying 1024. By 1024 matrix, time it, get the dot product, and put it in Z, and then time it. When I run this on my dedicated server equipped with an Intel i7 6700, a quad-core Haswell CPU, it takes 8 milliseconds. Total flops 2 billion. And total flops 2 billion. Yes, because 1,000 times 1,000 times 1,000 times 2. What's that? How many flops you will have? Yes. Total memory load 8 megabyte using floater point 32. Total cycles is 8 milliseconds times 3 gigahertz is 27 million total, 27 cycles. That's 18 flops per cycle, per core per cycle, or 250 gigaflop per second on hardware released in 2015, and that's a lot. Fair enough. How can a single core do 18 flops in cycle? On my Haswell server, NumPy uses Intel's MKL implementation of BLAST. Particularly, we care about how the segmentation SGEMM function is implemented. Okay, SGEMM is short for Single Precision General Matrix Multiply. General Matrix Multiply performs this computation and C equals to a scalar of times A times B, and then plus B scalar times C matrix. Each is specific to one of the Intel's microarchitectures. An example is Single precision general matrix multiply kernel Haswell, and single point precision general matrix multiply kernel Sandy Bridge. At runtime, the BLAST library will use the CPU ID. He doesn't explain that instruction to query the details of the processor and then call the suitable function. This will increase the size of the BLAST binary considerably since it's carrying around general matrix multiply implementations for many architectures, even though we ever only need one. Okay, to query the details of the processor and then call the suitable function. Looking closely at the relevant SGEMM kernel Haswell, the speed comes from using vectorized FMA. Vectors or SIMD, single instruction, multiple data stream instruction performs the same instruction on all entries of the vector input at once. We know that from the compiler videos, guys. Just memorize it. Anyways, FMA stands for fused multiply add. This means performing A equals A plus B multiplied by C by using a single fuse instruction. Sometimes this is also referred to as MAC, multiply accumulate. Alright. In my particular case, the VFM ADD instruction, it operates on three 256-bit long YMM registers, calculating YMM1 multiply YMM2 plus YMM3 and storing the result in YMM3. That allows the CPU to perform 16 single precision flops with one instruction, checking Agner-Fox instruction tables and uops.info. VFM add ADD has a throughput. Confusingly, this is the reciprocal throughput, meaning the average number of clock cycles per instruction for a series of independent instructions of the same kind in the same thread. Sure. At a latency of 5 cycles, this means we need to find 10 times 16 flops that we can schedule independently. Since the result of previous instructions is only available 5 cycles after they were started, this will be one consideration when writing optimized code. Grouping enough independent operations such that the CPU can schedule all of them at once, fully exploiting its instruction level parallelism ILP capabilities. So to conclude, Intel's BLAST library achieves 18 flops per core per cycle, where the theoretical upper bound is 32 flops per core per cycle. Pretty well. In reality, the implementation is even faster since we are also measuring some Python over here. And the time to start the OpenMP thread pool. OpenMP thread pool, what was this? And what is OpenMP? OpenMP is a strictly fork/join threading model. In some OpenMP implementation, threads are created at the start of a parallel region and destroyed at the end of the parallel region. OpenMP applications typically have several parallel regions with intervening several regions. Okay. Note how even though the matrices aren't that big, we're strongly compute band already. Loading 8 MB from RAM takes maybe 200 microseconds, assuming a memory bandwidth of 40 GB per second. For multi-threaded SIMD memory accessing, numbers from the Excellent Napkin Math project. Okay, So that's some average number he's using. If the matrices get bigger, we become more compute bound since we are performing 2n cubed flops per 2n squared loads, trying to recreate this performance from scratch. To spoiler the outcome, we'll end up with an implementation that performs 9 flops per core per cycle, but only works for matrices of a specific size. The goal of this post is not to write a competitive BLAST implementation, but to learn about common performance optimizations. I'm running this on a quad-core Intel i7-6700 CPU at 3.4 GHz. On a dedicated server, it has 32 KB per core, L1D the cache, 256 KB of pre-core per core L2 cache, and a shared 8 MB L3 cache. The compiler I'm using is Clang CLang. Come on, it's CLang. We port version 14.0. Benchmarking is done through Google Benchmark. Okay, so implementation time. Naive implementation. We have 4 seconds, 481 milliseconds. Naive implementation RCI plus compiler flags, 1 second, 621 milliseconds. And naive implementation RCI plus flags plus register accumulate is 1 second, 512 milliseconds. Cache over loop reorder RIC 89 milliseconds. Loop reorder RIC plus L1 tilting on I 70 milliseconds. Loop reorder RIC plus L1 tiling on I plus multi-threading on R and C 60. NumPy MKL is 8 milliseconds. Okay, naive implementation. Let's just start with a basic nested for loop. We have 2 float pointers. Interesting, I had never seen this in C++, but apparently that's a thing now. It's a constant. Then you multiply these, you plus it, you put it in that column. I guess. Excuse me. Record the matrix dimensions by templating them. This makes it easier. I'm not the best C++ programmer, so just take it as the face value. This makes it easier for the compiler to optimize, but makes the comparison against BLAST. Let me just do this 1 second. Since BLAST kernels have to work for all matrix sizes, in practice a good BLAST library will have multiple implementations of matrix multiplication implemented for different size ranges. At runtime, based on the matrix dimensions, it will decide on which one to use. However, fixed matrix dimensions commonly appear in practice, for example when just-in-time compiling a neural network where the batch size is known, plus the MKL. What is MKL? MKL CPU. And it's math kernel library. MKL math kernel. That's not how you spell kernel. Library. Okay. However, fixed matrix, the math kernel library implementation is so close to the theoretical maximum that it will serve as a good target. Compiled with CLang and default flags, this takes 4.4 seconds. The first easy fix is to adjust the compiler flags. First, we enable optimizations via -03. Then we tell the compiler to generate code that is specific to this microarchitecture. In our case, Haswell, via flag -march equals native. This allows the compiler to output code that may not run on CPUs of a different microarchitecture, making it non-portable. Lastly, we use -FFA AST -math allowing the compiler to do associative float math and promising it that there will be no knotted numbers and infinities in our program. Combine these flags, bring down runtime to 1.6 seconds, which may or may not be reasonable. See this post about the dangers of this innocent sounding fast math flag. Another straightforward improvement to perform the inner dot product in a register and only write out the result once the product is finished. So perform the inner product in a register. Okay. In a register, only write out the result once. Okay. So if you do this, you keep that in a register. But if you do this, probably you just keep loading it from. I don't know how it works, but I'm learning a lot. This is a slight improvement, down to 1.5 seconds. I tried figuring out if it was legal for the compiler to optimize evade the inner store, but couldn't get a definite answer. After inlining, the compiler could figure out where the pointers come from, and since they aren't marked as volatile, get rid of some stores. In any case, it's better to write the register accumulation ourselves by hand, instead of relying on the compiler. What? It's better to write the register accumulation ourselves by hand? Oh. Anyways, cache-aware implementation. Multidimensional matrices are represented in memory using a standard representation. For a more detailed explanation, dude, I'm itching to read this. Okay, this is gonna be next video. Please load. Damn. Ugly feet. But damn, this is the next video. Okay. In most programming languages, you expect the matrix to be row continuous, meaning that iterating through a single row by incrementing the column results in sequential memory access. In most programming languages, you expect the matrix to be row continuous, meaning that iterating through a single row by incrementing the column results in sequential memory access. Ew, I didn't know that. I mean, that makes sense, but how did I think it works? I don't know, but fair enough. This makes it clear why the inner most important loop of our matrix multiplication is very cache unfriendly. Normally, the processor loads data from memory using fixed size cache lines, commonly 64 byte large. When iterating over the row of A, we incur a cache miss on the first iteration. The cache line fetched by the processor will hold within it the next 15 floats as well, which is a good use of cache. However, for matrix B, we walk down the roads occurring cache miss at every step at 1024 rows times 64 byte cache lines, and this means we've loaded a total of 64 kilobyte from memory once we reach the bottom row. On my specific CPU, the L1D cache is 32 kilobyte large, meaning later cache lines will kick earlier cache lines from the cache. Once we reach the final row, the first row of A and B are gone from the cache, and computing the next dot product will start fetching all already. Okay, so it gets this, it gets that, but then I don't think I hold both of them, so it will kick both of this, but it should keep this. If that kind of makes sense. Useful cache line. So you want to keep this, you want to keep loading that. So to fix this, we reordered the two inner most look. Damn. This is crazy. Rows, inners, columns, results. You have the inner Uh, inner. So basically, it's just. Oh, so how he. Oh, wow. So he basically didn't care about a multidimensional, like reading 2 and 1. He's multiplying the size of the columns times the row, and he adds the inner. Genius, bro. Genius. The improvement is quite spectacular, bringing runtime down to 89 millis. Wow. A 16 times improvement. Our inner loops now iterate through B and C in a memory sequential manner. The only time we do a large jump in memory access is when our middle loop finishes and we need to fetch the first row of B again. Since we are now only computing a partial result in the inner loop, we cannot perform the accumulation in a single register anymore. In outer for loop, middle for loop, inner for loop, until middle loop finishes, partial results only. Looking at the compiled output, you know what you can do? I can make a fork from freaking George Hot's Tiny Grad and I don't know how fast those guys are, but what this guy did was a lot of architecture dependent optimizations, but he used a bunch of like compiler flags. At the same time, he used some hard code logic of how the computer works and just use that to that, which is genius. Absolute genius. Anyways, so what is this? Looking at the compiler output on a compiler explorer, this is great. The loop reordering also enabled vectorization. The relevant parts of the assembly look like this. With the naive loop order, the compiler was already using VFM add instruction, but only on a single FP32 at a time. And sure. Okay, I'm just gonna read these. This is my first time just saying this. VMOVUPS YMM1 YMM word pointer. Read. This is just. Looks hard. Yeah, so this is floor turn. It probably adds PS. Like, oh, maybe we can read these. Initial instruction: load 8 entries from the current row of B into YMM register. Okay, YMM is the register, obviously. And then you have to load 8 entries. In each instruction, multiply the current entry of A, YMM 0 times the entries of 0, C, YMM 1-4, and add partial results from C. And okay, store the partial results back to C's memory. So you remember the 8 entries we had, and then the YMM registers. You gotta put them back into this. You loaded them, put them back if you're a good person. And tiling. We just saw how reordering our loops made the caches happy about a lot of performance. Next, we'll cover a technique called tiling, sometimes also called cache blocking. To motivate this, assume this toy example of multiplying two 6 times 6 matrices and an L1D cache that fits 36 floats is fully associated. This means every cache line from main memory can be placed at any location into the cache. And this means every cache line from main memory can be placed at any location. Every cache line from main memory can be placed through a first in first out replacement policy should suffice. We haven't got there. Has an omniscient cache replacement policy. Okay. On level, where are we? 16. Okay, I gotta see what this guy's all about. is there one here? Oh, of course he's in Anthropic. And of course he went to ETH Zurich. And of course he has a master's degree. Alright. Compiler engineering intern, software engineering in Astero Institute. He's now in. Well done. Okay, so we got our little bit of rest there. Oh, my back. Excuse me. 16. And tiling on multiple dimensions. Similar to our tiling on the inner dimension, we can also perform tiling on the rows and eventually on the columns. There are dimensioning returns here for our small size matrices, but for larger matrices this makes sense. Each new dimension that we tile on allows us to make the work instead of our inner loops smaller while introducing extra overhead. RDIM, IDIM tiling, CDIM tiling, all that. Multi-thread and matrix multiplication. As the last step, we will enable multi-threading by using OpenMP. I remember OpenMP. You had to do something with. I had to do something with OpenMP. It's a programming language. OpenMP is an application programming interface that supports multi-platform shared memory, multiprocessing programming in C and C++ and Fortran on many. Okay, my bad. Let me make sure you guys see this as well. And all that gives a program is simple and flexible interface for developing parallel application for platforms ranging from Okay, so multi-threaded matrix multiplication. This was kind of expected. As the last step, we'll enable multi-threading by using OpenMP. To pick up a good strategy, it's important to consider the dependencies of each entry in the result matrix C. We want to avoid having to do partial summing between threads, which will either require atomic or locking. As a distant aside, the input dependencies show how recent deep learning transformer models can partition the two linear layers that are part of the transformer block across GPUs. Tensor parallelism with only a single MPI communication step. And needs atomics or locking. The first layer is the second layer is the column partition. The first layer is column partition on the weight matrix and produces column partition output. The second layer is row partition on the weight matrix and its output is MPI, all reduced sum into the final result. Partitioning are twice 6 times 6 multiply between, and this next. Okay. Result dependencies. One way to divide the work among threads without the need to perform communication is by partitioning the rows and columns. We split both the rows and columns into chunks of 4, giving us a total of 16 pieces of work, which we divide 4, 4, 4. Do you need to do that? You do need to do that. Do you need to do that? Some of them are repeating, aren't they? It's the exact same one and it's repeating. Maybe. I'm not sure why he's doing that, but anyways, one way to divide the work among threads without the need to perform communication is by partitioning the rows and columns. We split both the rows and columns into chunks of 4, giving us a total of 16 pieces of work to divide amongst 8 hyperthreads. Well, we have 4 cores, why are you not dividing it amongst 4 hyperthreads? I mean, that's a reasonable question I think I should have. No? No? Anyone? Okay, so he's tiling in. He's basically moving because these numbers just go. Each column is just the number of row. The next column is just skipping the row. And then 256. Eight times 8 times 8. That's 256. Sure. But did I just screw that up? I think so. Yeah. 8 times 64, it's 512. So it's 8 times 8 times 4. Eight times 4, because you're doing 4 rows times 4 columns, and that's 128. 8 times 8 times 4. That gives you 256. Yes. Anyways. Okay, so these are our original for loops. It's giving us the row tile, common tile, inner tile, the row tile, row, and then it pushes that many. Not sure why. Oh, I'm stupid. The thing is not 8 by 8. It's 1024 divided by 4. Yes. Yes. That makes sense. Sometimes happens. Even me makes mistake. Conclusion. Optimizing matrix multiplication is a fun exercise. It touches upon loop reordering, cache-aware reprogramming, and proper work distribution during multi-threading. Basic linear algebra subprograms. Implementation will probably also implement tiling for registers and multidimensional tiling for all caches of the L1, L2, L3 hierarchy, among a few other optimizations that we didn't cover here. While writing this code, it became apparent to me how easy it is to get lost while optimizing even a simple algorithm like matrix multiplication. You really need to have a strong mental model of the working of your CPU and a well-oiled benchmarking and testing setup to be able to iterate quickly. Note, there are other algorithms for matrix multiplication that have an asymptotic runtime that's faster than O(n) cubed, like the Coppersmith-Vinograd algorithm that runs in n to the power 2.3755. However, these algorithms have larger constant factors, making them slower for all commonly encountered matrix sizes. To my knowledge, no BLAS library uses them. Just for comparison, the 2021 MacBook Pro with the M1 Pro chip runs the same numpy code in 1 millisecond. If you use Apple's Accelerate BLAS implementation, the M1 chips have undocumented matrix assembly instructions that only Apple can compile for, which is where this speed up comes from. With OpenBlast, the MBP takes around 8 milliseconds. Similar AMX instruction but document are included in Intel Sapphire Rapid microarchitecture. I was led down this rabbit hole of optimization when I stumbled over Marek.ai matrix multiplication on CPU a few weeks ago. At github.com flame how to optimize generalized matrix multiply goes much farther and explains how to actually reach BLAS like performance from scratch. Wow. This is just wow. Okay, so we need to reiterate through these a little bit, but so basically understanding how the CPU works, understanding how your code works, and understanding how your memory works is a great way to optimize these things. Understanding how your compiler works is a great way to optimize these things. You have your basic linear algebra subprograms that are already written for you, but you can write your own stuff and make your things go faster. Yeah, which is fun. Yeah. Let me see if the tiling. So the tiling is our dimensional tiling. It's this way, that way. This goes this way, that way. Goes this way, that way. Y goes this way, that way. Tile size. Okay, maybe we should start here. Tiling on I iteration from middle for loop, inner for loop. Goes this way, goes down. Inner for loop goes this way and it goes down. And then middle for loop goes this way and it goes down. And then it goes basically how it goes this. Oh, very interesting. Because this, it puts it there. And because you're doing this, just kind of tiling. How does it make it faster? It makes it faster by you go this move, but this way. Oh, because he was using the multi-threading matmul implement. Yeah, I don't know what matmul is, but someone told me it's related to GPUs. I'll take you for the face value. Yeah, so he's doing that in program, and he doesn't want to have the data's intercepting each other. I feel like that's about it. Yeah. Alright, so that's it for this video. Thanks for watching.